So we've been looking at like lines and quadratics, which show up as like a parabola when you graph it. We're going to look at two other types of functions today. So two kind of like randomly shaped functions. First one's going to be an exponential function, which is kind of different than pretty much anything you've ever done before because the variable is now in the exponent. And typically, as we're going through and doing problems, we don't have the variable in the exponent very often. So this will be something kind of new. So example, they write it this way. I'll maybe switch to orange, try to make it pop off the page a little bit. But they'll say y equals b to the x. There's nothing really special about the letter b. I think they pick b just because it's the base of the exponent. But so if you wanted to, that doesn't make a lot of sense. We're talking about something like that there, like y equals 2 to the x is going to be one of these exponential functions. Fair enough? And we have two different types of curves for that. They're going to be generally one of two shapes. If you take a number that is bigger than 1 and multiply it by itself, it should keep getting bigger and bigger and bigger, right? Like 2 times 2 is 4, times 2 is 8, times 2 is 16, and so on. If you have a base of 4, so 4 squared is 16, 4 times 4. 4 times 4 times 4 would be 16 times 4, or 64, I think, if I did it right in my head. But the numbers keep getting bigger. So my first one is going to be, we'll say the base b is greater than 1. And for that, it's going to look kind of like a parabola, but it's not going to go through the origin. It's going to start up a little bit. Most of the ones today are going to have a starting point of 1. I wouldn't write that in because that's not always true, but we're giving you kind of the easier version of exponential equations today. But so it starts out kind of close to horizontal, but it should get steeper and steeper and steeper and steeper the further it goes. So if we have a number that's larger than 1 to the x power, the curve is going to look something like that. Now the graph is going to get smaller if what's true about b. And it's not just that it's less than 1, but it's between 1 and... Go for it.
0?
Perfect. Because if you have a negative number, and now you're doing exponents, like a negative number to the second power is going to become positive, but a negative number to the third is going to be negative again. So your graph would be like flipping all over the place. But if instead we have 0 is less than b is less than 1, so at the base of the exponent, some decimal like 0.2, 0.97, 0.18, some decimal between 0 and 1. It's going to kind of be the opposite of that first graph. It's going to cross up here somewhere, and it's going to start out dropping really fast. So it's going to start out real steep, but then kind of level itself off. And it'll never actually touch the x-axis or go below the x-axis, but it'll just kind of keep getting closer and closer and closer and closer to it. So something like that. It will cross the y-axis, but not the x. Fair enough? So those are the two types of exponential curves we can have. Well, if we take this, a little bit later on in your math careers, you'll come up with actually writing the exponential equations. For now, we'll pretty much just kind of give them to you. So I'm going to say this equation there, y equals 2 to the x, works if somebody in your PE class has one bacteria on their foot and they don't wash it for forever. But they start with one bacteria, and the number of bacteria will say doubles every day. Then if x is the number of days, this equation here will tell you how many bacteria are on their feet. Fair enough? So let's say that happened perhaps today in PE class, and we'll pretend it's not quite this close to the end of the year. But one of you, who we won't mention, who has a piece of bacteria on their foot, next week, 2 to what power? 7. Because if x is the number of days, 7 days later, next week, Friday, you show up for PE and they take off their socks and start walking around on the locker room floor. What do you think that number is? Don't put it in a calculator yet, but we're talking like 100, we're talking a couple hundred, a million. What do you think?
48.
48. So if we do a 2 to the 7th, punch in my calculator here, I get 128. Yeah, better than a lot of people's guesses, 128. Now let's say you invite them over to your house, because it'll be summer vacation 2 Fridays from now. So 2 weeks from now, it's going to be 2 to the 14th, because 14 days will have gone past. Guesses on the number.
1,048.
So 1,000, a million. Some people are doubling it.
6,000.
Don't tell me I want to figure it out.
Oh,
16,384.
Wow.
Should we do 3 weeks just for kicks?
Nah. Yeah.
If we do a 2 to the 21st,
21st.
now I have 2,097,000, so 0,97152. You'll notice the numbers are going up faster and faster and faster, right? And that's the point of this curve I was trying to draw here, is that as you go through and look at these, exponential curves get steeper and steeper and steeper the longer you go. And that's why, if I'm going to give you one bit of financial advice, it'd be this. There's this thing called a Roth IRA. Typically, when you put money in your retirement, you don't have to pay taxes on it, but you have to pay taxes on the interest. When you take it out, you have to pay taxes on the interest. There's this Roth IRA where you pay taxes on the money you put in. There's a limit to how much you can put in a year, but then you don't have to pay interest on the taxes. So a lot of people, they get out of high school, it's like, well, put money in retirement. No, I'm saving money for college. You get out of college, I need to pay off my college loans. So they don't put money in retirement. And then they buy a house. Well, I could put money in retirement, or I could try to pay off my house faster. And they have kids, and kids are expensive. So a lot of people, they just put off saving for retirement. And then they get to be like 50, and they're like, holy cow, I actually kind of want to retire at some point. And then they start putting money in, like when they're, say, 50 or 55. Here's the problem. Money, when you invest it, grows typically in an exponential sort of curve. So if you start investing here, 10 years later, you don't have that much more money, right? You kind of waited too long. Or if you can start putting money away when you're 20, well, then you're 30, then you're 40, then you're 50, then you're 60. If you start early, you get to the steeper part of the curve where your money actually has time to grow. And I should clarify, I'm not saying the point of life is to become rich. I'm not saying the point of life is to retire so you can just sit by the cabana and drinking your Mai Tai. I don't even know what a Mai Tai is, but so I'm not saying it's that. I think God calls us to do work and to do good, but a lot of people, when they do choose to retire, well, then it gives them more time to do good, or to have money later in life to do good things with. So, but yeah. So consider that at least. Okay, moving on. Termite spray kills 40% of the termites. I said typically we'd give you the equations. This time I didn't. But if we want to figure out how many termites are left, so I have termites. I'm going to spray for them. How many are left after one spraying? What percent?
60%.
Nice. If I kill 40, I'm left with 60. So my equation is going to be y equals 0.6 or 0.60 if you want it to look like 60% to the x. Where x is going to be the number of sprayings, 60%'s left. Now, what I'm doing is I'm kind of doing this, and you don't have to worry about this, but I'm kind of, do you agree you could look at this as 1 times 0.6 to the x? And 0.6 is 60%. 1 is going to be what percent? 100. So I'm kind of saying I'm starting with 100% of the termites. I'm killing 60% of them every time. Fair enough? So if our answer becomes, I'll come back to that in a second. If our answer comes out as being a 0.2, that means you have what percentage left? 20% left. So okay. So all right. So if we have 4 sprayings, I'm going to ignore that blue 1 in there and just say, okay, 4 sprayings would be y equals 0.60. I'm ignoring the 1 because it doesn't matter. Is that fair? You could punch in that way, it'd be fine. But it's going to be 0.6 to the 4th. So 0.6 to the 4th. And I get 0.1296. 0.1296, which is what percent?
12.96%.
Very nice. 12.96%. If you want to round it to 13%. Please don't round it down to 12. So if you're going to round, make sure you round correctly.
How do you do it to the 4th? I can't do that.
Okay. For punching that into a calculator, so we're used to the x squared button. Most of your calculators, you do 0.60, then you should have a key. I think they call it a caret. I think it's up above the division for a lot of them, or near the, nope, it's on the left side on mine. And then a 4. So this here is the button you could use for the exponent. Some people have like a y to the x or an x to the y key on their scientific calculators. Something like that. All right, that's the first half. That's the exponential functions. We all right for exponential functions? Okay, awesome. Next step,
It's because of our riddle and stuff.
Sam made an awesome observation. When on the termite one, he said, but you're never going to get rid of all of them. So this equation that I did for termites technically doesn't work because he's right. If y was the number of termites or the percent of termites and x is the number of springs, this thing here never reaches the x-axis. So if that equation actually were true, you would never actually kill off all of the termites because y would never hit 0. It just gets closer and closer to it.
You didn't do anything.
Is step functions. Ooh. The entering card. We'll try the blue. Okay, so this thing here, step functions. Step functions, parking garage.
Let's go.
Parking garages, you go downtown, you go to the museum, like my son in his kindergarten class did today. You pull into the parking garage, you punch your ticket, you go in, and as soon as you go in there, if you realize, oh, I forgot the free pass in the museum, you drive to the exit, they're going to make you pay, right? So as soon as you go in, you pay $2 for each hour, so you're going to pay $2 up to an hour, and then once you, well, let's just, okay, do this. I'm going to say up to 4 hours. So my x-axis, I'm going to do 0, 1, 2, 3, and 4. On my y-axis, I'm going to go up to 8. So I'm going to say 2, 4, 6, and 8. And my y values are dollars. My x values are hours. You could say time if you wanted to, and h in parentheses. You okay for the graph? All right, so now here's the thing. If I park there for 0 hours, do I have to pay anything?
Nope.
Nope. So I'm going to take, and we'll come back to kind of y in a little bit, but I'm going to put an open circle right there. Because if I park for 0 hours, I don't have to pay anything. And by the way, this y value would be a 2. But do you agree as soon as I've been in there for 15 seconds or 1 minute or any amount of time, I'm going to have to pay my $2?
Yeah.
Now, do I still pay $2 if I'm way over here really close to 1 hour?
Yeah.
Yep. So this first part here can't be something that goes up because I pay a constant $2 for that time. So it's going to just be a horizontal line that goes over until this x value of 1. It's just a horizontal line there. Does that make sense?
Yep.
And if I can punch out, if I can get out of that parking garage in 59 minutes and 59 seconds, I still pay $2. And I suppose if it's exactly 1 hour, I still pay, because we said $2 for each hour. But as soon as I'm there for 1 hour and 1 second, I have to pay 4. So we can't have, technically we can't have my graph start right here at $4 and at the 1. Because then the graph would say you need to pay $2 and you need to pay $4. So right here where my red dot is, I need to have a open circle.
Sure.
Because the open circle is saying, well, when x is actually 1, I'm still paying the $2 right kind of here at the bottom. That number there that I'm making bigger. But now as soon as I'm a second over 1 hour, now I pay $4 right up until my 2 hour mark. And at 2 hours, I'm still at 4, but as soon as I'm a tiny bit over, so I do an open circle at an x value of 2 and a y value of 6. And now as soon as I leave that and head into like 2 hours and some minutes, I pay $6. And then the very last one, open circle at the 0.38 and over to 4. So it kind of looks like steps, which is kind of probably why they're calling it a step function. It's all these individual steps going up. Does it make sense logically to you, though? It is possible that these open circles and closed circles will be switched. And I wouldn't mess up your notes with this, but you'll see some that have like the open circle on the right and the filled in circle on the left. So as you go through and do these, you just have to kind of figure out, well, when it's right at this x value, is it an open circle or a closed circle? But it'll generally look, once you figure out is the open circle on the left or the right, then it just repeats for the rest of the time. And that should be everything, unless there's questions you guys have for me.
Yep.
Good?
Let's get to it.